Hello everyone, my name is Anjali Jain and I'm working on container networking solutions for Intel.
Hello, my name is Nupur Jain, and I'm part of Intel Container Networking team.
So we're going to be sharing with you guys our findings and analysis with respect to network scalability in a current data center. Here is an agenda. We're going to first talk about container network function and interfaces that are currently used, their limitations, and then talk about some solutions. We'll conclude by presenting some of our P4 code, which shows data plane offload of these network functions that are used in container networking. So here is the overall view of container networking deployment in a data center. What we see is there are 5 important elements. Two of them right on top, the edge router and the cluster router. These are common networking functions used in a data center, not specific to container networking. And so we are not going to focus on these two elements. The problem and the solutions are well understood in the space. Our talk is going to cover mostly the challenges, limitations, and solutions for a node uh, in container networking deployment. Uh, the first network function that comes into play is a load balancer, which is deployed with DNAT and connection tracking. And at present, all solutions run in user space or in kernel in software. And then we talk about the L4, L7 classifier, which is the last mile classifier to a container interface within a pod. And then the container interface itself, the ones that are deployed currently, and what are the possibilities. So, a quick summary of the current state of deployment. What we see is in a data center, there's a huge need for scalability, to have tens of thousands of containers on a node. What we also see is that the hardware in terms of platform and NICs, FNIC and SNIC have really scaled in terms of bandwidth, programmability, resource scaling, to support multiple virtual interfaces and things like that. So there is all the hardware capabilities, uh, you know, uh, already there. But what we see is there isn't effective utilization of these hardware capabilities to make the container networking deployment ideal. So we are going to focus on how to effectively utilize these hardware resources. So here is what we see as the existing interfaces for a container pod and also the container interface itself. What we see is typically the pod interfaces are stacked Netdevs like MAC VLAN, IP VLAN assigned to container namespaces. And in some cases, instead of stacked Netdevs, people have also used SRV interfaces to provide, some amount of switching offload into the hardware. Both these solutions, have some challenges. The first one being, does not benefit from hardware classification capabilities, and it's mostly software solution. The second one, even though there is an offload into the hardware because of SRV VF interface in play, it's too heavy an interface to use for a container deployment. So the most important question that arises is, why do we need to hardware accelerate these interfaces? The reason to hardware accelerate container interfaces is to avoid latency and jitter challenges. which get introduced due to kernel to user space context switching, like in the present AFXDP memory model. Um, and because of this latency and jitter is where there is a lot of underutilization of the CPU resources. And, lots of CPU and memory on a server node is used in doing solving the scheduling and memory management issues. Plus, without hardware acceleration or offload, we don't get to container level isolation. So here is, a solution for the fifth element that we spoke about in our first picture, which is about the container interface itself. As part of the solution, what we see is there are 4 things required to scale. One is a lighter weight virtualization provided by platforms like the newer versions of VTT, which is SIOV, which provides assignable device interfaces. That's one part of the solution. The other is, latest enhancements in the Linux kernel with respect to auxiliary bus and subdev framework, which lets one to kind of dedicate resources, per Netdev pod and provide classification benefits from the hardware. The last and then there is the last element of the solution is being able to provide container interfaces in user space, and that can be achieved by enhancing AFXDP raw socket to have a newer memory model for pass-through. Once again, all of this depends on thousands of hardware queues that are provided by present FNICs and SNICs. And so the proposal here is that the boxes in orange that are shown here, there are some enhancements in software needed to take advantage of both the platform virtualization capabilities as well as the the hardware's ability to classify more deeply. So this is the 4th element of the problem domain that we looked into, which is of the last mile classification to a container interface. At present, this classification happens in software, and there are, powerful NICs out there that can actually provide a very programmable classifier, which is, at an L4, L7 level, and forward the traffic directly to, say, a container interface using dedicated queue pairs. So there are 2 possibilities in the space. One is, AFXDP raw socket gets bound to an individual queue pair, and hardware provides sideband filters or inline filters to route the traffic to these queue pairs, as was mentioned in the previous slide. The other solution is that we do only offload of the classification, but not of the forwarding. In this case, the hardware can provide flow mark or a 32-bit hash value in the prepended data meta, like in the AFXDP buffer, and that can then be used by software to do the forwarding. So more desirable is to be able to do classification and forwarding in the hardware, but in some cases, if there are challenges for having enough queue resources, classification is still a really good benefit. Nupur?
QProxy is a key component of Kubernetes deployment. Its role is to load balance traffic that's destined for a service to correct backend pod. QProxy can run in one of the three modes: eBPF, discussed later in the slide, Iptables, or IPVS. In Iptables mode, QProxy attaches rules to the NAT pre-routing hook to implement its NAT and load balancing functions. The problem statement here is that the chain of rules roughly grow in proportion to the cluster size. IPVS uses IPset, which is more designated towards load balancing and firewall use cases. It uses hash of collection of similar rules, uh, like IP addresses. Since it's a hash, it offers better performance. The problem again is that the packets that take IPVS route, they cannot be used along with another solution that needs IP tables for filtering and classification. So two such solutions have to be evaluated together. Connection tracking happens to be the core feature of Linux kernel. For both modes, QProxy uses connection tracker to match packets against existing connections. Over the years, kernel community has made contract robust to sync flats by using like syncache, fixed hash buckets, recycling of oldest half open TCP. But connection tracker has a max size. And if it fills up, connections will typically start getting either rejected or dropped. There is no flexibility or programmability in contract to select algorithms or fields to hash on. Kernel solutions do not provide a way to selectively choose a new algorithm for consistent hashing like maglev, which are very use case based. Kernel overall is not very flexible. Latencies due to IRQ processing, context switching, slow API configurations are also limiters of performers. So community took another approach, which is eBPF and XTP. It's more performant than the kernel. It's designed as an alternative for DPDK. Codes can be injected into the kernel by changing kernel behavior altogether at TC and XTP hooks. It gives the ability to reload programs on the fly. There are a lot of plugins today that make use of XTP eBPF solution to implement networking functions like network policy, encryption, load balancer, but there is a limitation as well. These are not hardware offloadable to ASICs. Metronome solution exists, but it exists with the NPU general purpose cores. We think a ASIC built with more purpose cores and context aware caches provide a better scalable and performant solution. Then there is maps which are exist, which provide a way for user space to send configurations down to kernel space, and they lead to context switching. So here's a small experiment we run on Cilium implementation of eBPF. We set it up in two modes. One was the XTP mode, another was no XTP mode. Cilium usually does connect time load balancing by hooking into kernel XTP-TC hook on the receive. When a client tries to connect to a Kubernetes service, Cilium intercepts the connection and load balances with DNAT to directly connect to the backend pod IP. What we observed in this this experiment that we ran was there wasn't significant performance improvement of XTP over non-XTP solution. And this may be because we kind of suspect that XTP path may not be taking advantage of hardware XTP redirect queue designed to send packets to another interface. There are more results at the end of the slide. So this slide is our solution to a complete end-to-end hardware acceleration path from the control plane offload to container network interface. We looked at existing Kubernetes deployments and identified the offload points and flow based on a study of Antrea and Cilium plugins. The control plane logic will have to be translated to a P4 program with static mapping to match action tables, registers, and constants. Once our programmable pipeline reflects the same logical view with optimized hardware resource mapping underneath, the plugin layer or adaptation layer will be able to statically map control flows using runtime API calls to our hardware. This will give a significant performance boost. P4 compilers today take care of effectively optimizing and removing loops and mapping to resources offered by the architecture. Verifies, the verifiers take care of memory boundary checks, programming semantics, and mapping. The picture also depicts the device plugin. Multis, SRIOV, and ADQ plugins have already been shared by Intel for the wider community use. We foresee SIOV plugin to be published as well. This picture also shows the Intel IO acceleration technology that brings all goodness together related to Intel quick data technology, direct cache access, extended MSIX, receive side coalescing, low latency interrupts. Besides all this, the assignable device interfaces, as discussed earlier, and also using requester ID and pass it to identify the address space associated with the hardware cube, bring in both platform scalability and a throughput increase. So here are some sample P4 code for the cases we have already discussed. So this depicts a QProxy. QProxy does a five tuple hash for every new connection and then maps it to a service backend. The packets are then DNATed to this particular backend. CT preserves this mapping for all future packets. A packet is dropped if no backend is found. So this whole program has been implemented using PSA extern called action selector, which helps select the endpoint, and then using the fair hash algorithm, it will pick one of the backends and then send the traffic to that one. This picture is our P4 implementation of a firewall, which is both stateless firewall as well as stateful firewall. We are suggesting to completely offload CD code to the hardware using a P4 program. If connection does not exist in the initial stateless firewall, it will be added reactively. Timer is started on connections to remove stale entries and flush out old half-open sessions. P4 provides the flexibility to program table size and pick algorithm and fields for different use cases to hash on. In this example, if you look, there is a CD aging table miss where if the flow ID is not found, we allocate a new flow ID and add reactively an entry to the CD table. The timers are also started to clean up any stale entries and also to time out half open TCP sessions. Anjali?
Thanks, Nupur. This is the last part of the P4 sample code that we'll talk to. This is, implementation of the last mile classifier using L4, L7 fields. And in this code, you see, there is an exact match, a table matching on L3, L4, and L7 fields like the quick CID. This is a little bit more, advanced classification that, there are devices out there that can actually provide it, but, there could be devices that you know have limited you know parsing depths and things like that. Uh, so coming back to the opens and conclusions. So what we noticed is not every BPF program can be hardware offloaded, and we are looking into how best to map them to P4. We also are looking for community support in converting some of these XDP implementation to P4 programs. Uh, uh, Another angle is we might need some P4 extensions to the language or externs for complete packet transformations, such as crypto checksum packet replication, and these are being looked into. So in conclusion, what our journey for trying to find out the bottlenecks in container networking deployment led us to this final uh, um, uh, view that the the standard container control plane software can be used as is with no or very little modification, whereas uh, the container interface and pod would need enhancements in software to take advantage of the hardware isolation and resources. We also noticed that the software support for the lightweight virtualization needs some enhancements as well in the MMU code. The last one is about taking advantage of the programmability of the FNIC and SNIC for offloading network functions, and that is a big task as well, and we're focusing on achieving this. So that was it. Hopefully the talk was useful, and reach us out if there are any questions.
Thank you.
Thank you.